Welcome. Today, we are going to do something slightly different from whatever we have been doing so far. So far, we have been looking at momentum flux in a very rigorous fashion in various coordinate systems, and all have very many applications. We have been looking at some fundamental aspects which can be applied to pretty much anything under the sun as long as it is applicable. Today we are going to look at something called dimensionless numbers, and in the context of non-dimensional analysis. The dimensionless numbers we have already seen. The first dimensionless number that we saw, if you recall, was the Reynolds number, rho v d by mu. We saw that a long time ago, or even before that. I think we had introduced some non-dimensional variables, even in mass flow, mass flux situations, and so on. There are various advantages to using non-dimensional numbers or dimensionless numbers. It makes the solution general enough. Does not at first go. It is you get an overall picture independent of the actual dimensions of the system. The solution becomes very general. All that we have seen. Okay. Apart from that, there is a certain kind of an analysis that you could do with dimensionless numbers, which give good insights, and especially for design and operation purposes, when things are not fully understood. Okay, so I'm going to show you an analysis based on non-dimensional numbers or non-dimensional analysis, and at the end of it, you get a certain relationship, which is pretty much the same relationship that we got through an involved understanding of the problem. So even if the involved understanding is difficult at that point in time, you could do a non-dimensional analysis, get to the point of the relationship between the variables, use that relationship to design whatever you're going to design. Engineering typically doesn't wait for a complete understanding. We'd like to use things, okay? And then many times we don't know why it works, but it works because, intuitively we have figured out that it works this way or through experience. And then we try to understand the fundamentals at the molecular level and so on and so forth as to why things happen a certain way, even in engineering systems. So, for us, the use aspect is important. And this non-dimensional analysis significantly helps in getting at relevant expressions that can be used even without fully understanding the underlying mechanisms. Okay. I think it's useful to know this in the context of this transport course. So let me present this to you. We've already seen the Reynolds number, rho v d by mu, and it has no dimensions, of course. And as I mentioned just now, there are various advantages in using non-dimensional quantities. The relationships, equations in terms of non-dimensional quantities are more general in applicability. And an example is given here, irrespective of the density, the particular density, the particular velocity, the particular pipe diameter, and the particular viscosity in a given situation. As long as the Reynolds number, which is a combination of those quantities in a certain way to provide a non-dimensional number, is less than 2100 for pipe flow, okay, the flow will be laminar. Okay, that's something very powerful that we get. Now we're going to look at this powerful methodology that I mentioned that helps us to obtain useful relationships for design and operation. And the basis for this methodology is something called the Buckingham's pi theorem. Okay, that's the mathematical basis. So there is a certain mathematical basis on which we work on to get to this. This part is not going to be as rigorous as things were earlier. When there things were nicely understood in terms of a certain framework that we had, and therefore we could do rigorous stuff. Most things when we start out are not understood. Okay. And thereby we need to figure out ways of getting things done with partial understanding. So slowly in this chapter, we are moving from very rigorous aspects to not so rigorous aspects, but very useful aspects for design and operation. So we are kind of covering the entire spectrum. This is somewhere right in the middle. We are going to go do a little bit of back and forth. We are going to do this, and then we are going to get back to some rigorous stuff, and then get back to a macroscopic view, which is more of uh, not so rigorous analysis, but very useful analysis. Okay, so there we hand wave a little bit, but we get very useful relationships. Anyway, let's do this now. This is the right place to do this in this course. The Buckingham's pi theorem formally states this: if there are n variables in a problem, and those variables contain m primary dimensions. You know what the dimensions are. MLT could be one of the set of primary dimensions. You could have many different combinations, as you know, but let us stick to the simplest one, MLT. Okay, you could have F and something else also, right? But let us just stick to the standard ones, MLT, for this. But this formulation is applicable for any m primary dimensions. And if this is the case, then the equation relating all the variables will have n minus m. N is the number of variables, m is the number of primary dimensions, n minus m dimensionless groups. So we are after an equation that contains n minus m dimensionless groups that relates the various variables here, and that would be helpful for design and operation. These dimensionless groups are called pi groups, and mathematically speaking, you would write the same thing as a function of pi 1, pi 2 and so on till pi of n minus m equals 0. Okay, that's a mathematical representation. The important thing to note here is that the pi groups must be independent of each other. Okay. So this is the mathematical formulation. We are going to base our development on this mathematical formulation. But we are also going to use certain practices that happen to give us easy results, okay, or results in an easy fashion. So this has been proved time and again. We may not have a mathematical basis for why that practice provides us with information. That's what I mean. We are going to slightly relax the rigor aspect in this part of the course. What it means to say that the pi groups must be independent of each other is that it must not be possible to express any pi group as a combination of other pi groups. Okay, it will become clear as we go along. Just let us see this once more. It must not be possible to express any pi group as a combination of other pi groups. Okay, that's good enough. As we go along, the significance of that statement will become clearer. We need dimensions and we need the relationship between dimensions and quantities. So let us review the relationship between dimensions and quantities. You already know this from high school, so let us just review it quickly. You could view some of these as fundamental, such as mass is m, the dimension of mass is m, the dimension of length is L, the dimension of time is t. For flow geometry, you have the area L squared, length into length, volume is L cubed, and in the kinematic aspects, velocity is L t minus 1, acceleration is L t minus 2, kinematic viscosity is L squared t minus 1. Kinematic viscosity is viscosity divided by the density. That is L squared t minus 1. You can work it out and check whether this is indeed the case. For a dynamic situation, we have force is mass into acceleration, ml t minus 2. Pressure is force per unit area, therefore m L minus 1 t minus 2. Work is nothing but force times distance, therefore m L squared t minus 2. Energy is the same as work in dimensions, ml squared t minus 2. Power is work per unit time, therefore ml squared t minus 3. Momentum is mass into velocity, m L t minus 1. Density is m L to the power of minus 3. Viscosity is ml minus 1 t minus 1, as we have already seen in the beginning of this chapter. Surface tension we saw in the context of capillary flow. It's force per unit length, so force is ml t minus 2, so this is m t minus 2. And that is, it's good to keep this in mind, or you can make a copy of this table, keep it next to you. You can refer to this whenever you want. The emphasis on this course, in this course, will not be on memorization. Okay, that's never the case, especially when you have these complex equations. There's no point in memorizing those. You need to understand, you need to go from one point to another in a seamless fashion. That is more important than memorization. Memorization, of course, it's a good skill on its own. It's just that it may not be very relevant for this particular or some aspects of this particular course. Memory is certainly relevant anywhere. You need basic memory, otherwise you don't even remember each other's names. Basically speaking, you won't even remember basic things. So I'm not saying memory is not important. It is important. Only thing is that memorization at the cost of understanding is certainly a no-no in this course. Okay, now let's get back to this method. Let us apply this method to a situation that we already seen, as I mentioned earlier, to get an expression for the pressure drop, the delta P, in a straight pipe. We already have an expression for it. Let us see how we get to pretty much the same expression with just the dimensional considerations. No flow, nothing. Okay, just the dimensions. So this is a situation here. We have, let us say, a horizontal pipe of diameter d. The fluid of density rho and viscosity mu is flowing with the velocity of v through the pipe of length L. Okay, so this is what we have here, and the pressure drop, you can say, is expected to depend on these properties. Okay, even without too much insight, you can say that you can expect it to depend on these properties or these quantities, these parameters. Okay, or in other words, mathematically speaking, a function of all these quantities here, delta P, dl rho mu v equals 0, mathematical representation. The set of variables within the brackets is called the recurring set here, and the number of variables here is 6, 4, 5, 6. Number of fundamental dimensions is 3, and from practice, Buckingham pi theorem itself, the number of dimensionless groups is n minus m. Therefore, we expect a relationship between 3 dimensionless groups for this case. Okay, that's what we get from the Buckingham pi theorem, mathematical theorem. Now, to apply this method, 2 conditions need to be satisfied. Okay, that's been found from practice. Don't ask me for a basis for this. This works. The first one is that each of the fundamental dimensions must appear in at least one of the n variables. That we must make sure. Okay, and then it must not be possible to form a dimensionless group by using some of the variables themselves or the variables raised to some powers within a recurring set. Okay, you know what a recurring set is, the set of those variables that we are considering, 6 in this case. So let me read this again. It must not be possible to form a dimensionless group by using some of the variables themselves or variables raised to some powers within the recurring set. We have already seen what a recurring set is. Therefore, we cannot choose L and D together, okay, from that recurring set of 6 variables, because if you just do L by D becomes dimensionless. That cannot happen. It must not be possible to form a dimensionless group by using some of the variables themselves or variables raised to some powers. And you cannot choose delta P, rho and V together, because delta P by rho V squared becomes dimensionless. Okay, so if you leave out these and if you draw on experience of others, that it is known that the recurring set must contain 3 or the same number of dimensionless groups, must contain 3 variables that cannot themselves be formed into a dimensionless group. Okay, so we are looking for 3 such things. So let us look for 3. This comes from practice. Okay, there is no fundamental mathematical theorem which says this, but from practice we know that the recurring set must contain 3 variables that cannot themselves be formed into the dimensionless group, and this 3 is the same number as that of the number of dimensionless groups. So we have to choose 3 variables. Let us choose D, V and rho. Okay, so by themselves or in some combination raised to some power, they cannot form dimensionless groups among these 3. Okay, you can verify, you can check and see. This is diameter, length, this is velocity, and this is density. Now let's start the process. The dimensions are, for d it is L, for v it is Lt minus 1 velocity, for density it is ml minus 3, okay, ml minus 3. Now the procedure starts. We'll rewrite the dimensions in terms of the chosen variables. What do I mean by that? We write L equals d because this is the same. We write m as rho d cubed. Okay, you take rho and you take d cubed. This becomes L cubed. This is L power minus 3, L cubed, that cancels out and it leaves back m. So m can be written as rho d cubed in terms of the chosen variables, and t can similarly be written as d v power minus 1. V power minus 1 would be L minus 1 t, and this one would be L. So L minus 1 would cancel out and t would remain. So you get t as d v power minus 1. Now let's take the remaining variables. The remaining variables in this recurring set are delta p, L and mu, and we'll take them one by one. And we will write them in terms of, let us write the dimensions first. Delta p is ml minus 1, t minus 2. Okay. So in terms of the variables, or even before that, delta p times the inverse of this, delta p times the inverse of this must be dimensionless. Okay. So this has the dimensions of L, ml, t minus 2. So L minus 1 t minus 2, that is ml minus 1 t minus 2 times ml minus 1 t minus 2 inverse would be dimensionless. So delta p m minus 1 L t 2 squared is dimensionless. Therefore, the first pi group, dimensionless group, is nothing but delta p. M is what? Rho d cubed. Okay, rho d cubed to the power of minus 1. L is what? D here. So d is just d. And t is t squared. T itself is d v power minus 1. So d v power minus 1 squared. So you put all this together, you get delta p by rho v squared. So this automatically turns out to be one of the dimensionless group, the first pi group. We need 3. Now let's consider L. L is just L, therefore L into L power minus 1 is dimensionless, and therefore same procedure as earlier. The pi 2 would be L by d. And now if we consider mu, the third variable, mu is m L minus 1 t minus 1, therefore mu times the inverse of this must be dimensionless, which is m minus 1 L t must be dimensionless. Therefore, pi 3 is mu times m is nothing but rho d cubed to the power of minus 1. L is nothing but d, we are writing in terms of the variables, and t is nothing but dv per minus 1. Okay. So this must be dimensionless, that's the third dimensionless group. And this turns out to be 1 by the Reynolds number. You work this out, mu remains, you have a rho here, rho per minus 1 here, d power minus 3 dd, 1 d comes to the bottom, and here you have v power minus 1 that comes to the bottom. So this rho v d by mu is Reynolds number, and therefore this is 1 by the Reynolds number. Good. So now we have our 3 dimensionless variables. From the Buckingham pi theorem, we know that function of all these 3 equals 0, or we can write this as delta p by rho v squared pi 1 equals the function of pi 2 and pi 3. So delta p by rho v squared is a function of L by d, 1 by NRE. Or you could write this in a generic form as delta p by rho v squared. We are giving it a certain functionality. Some constant here, L by d raised to the power a, 1 by NRE raised to the power b. Okay, this kind of a formulation happens to work. Okay, so some functionality, it's general k, and you're raising it to a certain power, you're raising it to a certain power. As long as you find the powers appropriately and k appropriately, it should work. There's nothing wrong. There's no reason why it should not work. So this is the relationship between these variables, And notice, by a mere dimensional or dimensional analysis, as it is called, involving non-dimensional numbers, we know the form of relationship between the relevant variables, and that is powerful. Okay, so even if you don't understand the process, you can do one such thing for design and operation, which relates these variables in for the system that you are interested in. And now let us check the validity. We have this relationship from dimensional analysis. We have already seen that in pipe flow, the volumetric flow rate is nothing but pi delta P by 8 mu L R power 4. Okay, this is our Hagen-Poiseuille equation. Or flow rate is nothing but area times velocity, area constant area, or area times velocity is flow rate anyway, AV times pi delta P by 8 mu L, and I am writing this in terms of the diameter d by 2 power 4. So you cancel the terms, this is pi d squared by 4 and pi delta P 8 mu L, you cancel the various terms, then you get delta P equals, delta P is here, you cancel the various terms, you get 32 times mu V by D L by D. Okay, so mu V by D L by D, and therefore delta P by rho V squared can be written as 32 mu V, rho V squared, right? So mu by rho Vd times L by D. So you get 32 times 1 by NRE L by D from a perfect relationship. Okay, compare this to this. Delta P by rho V squared is K L by D per A 1 by NRE per B. So our K was 32, A is 1, B is 1. Okay, so just by a dimensional analysis, we get a relationship which is actually the form of the relationship is the same, which is a very powerful thing to know. Then you can do a couple of experiments to know the constants involved. In this case, 32 is K, and A and B are 1 and 1. You can get out from a couple of experiments by fitting the data to this, and then that you're all set to go for design of all related aspects. Okay, so that is the power of dimensional analysis involving non-dimensional numbers. I'm sure this will become useful at some point in time. I think that's all I have for this lecture. Let us stop here and continue when we get back. See you in the next class.